Hi, this is Liang.
Hi, I'm Guanghua.
This video is the presentation of subject 32933 research project. In this video, we will introduce and demonstrate our research for this subject, which is the vibration-based particle swarm optimized fuzzy controller with application to boundary following of mobile robot simulation environment. Our presentation have five parts. First, we will discuss the topic of our research, which is the optimization method of robot controller training. Second, the problem and solution will be discussed. Then we'll talk about the methodology we use in our research. The evaluation results and the video demonstration will be discussed afterwards. And finally, we will give the conclusion of our research. Our topic is the optimization method of robot controller training. We need to explain the four major concepts in our research. The first one is what is the robot and VBot's environment. The second concept is the wall-falling behavior. The third concept is the robot control, which included the definition of a fuzzy controller. The fourth concept is the controller training optimization. So what is the robot and the robot's environment? In this picture, we can see it is a screenshot of the software VBots. In the center of this picture, there is a Pioneer robot, which have two wheels, a LiDAR sensor, and 8 inputs. In these pictures, the left four inputs are used for gathering data. And the white area in this picture are the obstacle or the wall. The goal of this training is to let the robot execute a wall-falling behavior. So what is the wall-falling behavior? We can see from this picture that the robot stayed in the initial position here, and it is expected to go around the obstacle for more than one round. So the goal of the training is to enable the robot to execute this wall falling behavior. So how the robot is controlled? This training environment will generate some fitness values. This fitness values is the inverse of the number of time steps that the robot has run until fail. These fitness values will be put into an algorithm, the optimization algorithm, to tune the parameters of the fuzzy controller. This fuzzy controller will output a steering angle or wheel speed that control the robot to execute the wall-falling behavior. After the training, the robot will execute the falling behavior and go the trajectory shown in this white arrow. So what is the controlling training?
You can see is this video. It shows the in the initial, this fuzzy controller have bad performance, so the robot can't achieve the wall-falling behavior, and then the performance is improved, so the robot can move around this obstacle and run more than before. So this is called as the controller training. So actually the controller is a kind of fuzzy controller which is achieved with the fuzzy neural network. The fuzzy neural network is a three-layout neural network which have the input layer, fuzzy rules layer, and output layer. The input layer will get the reads of the LiDAR sensor as the input, and the output layer will output the steering angle for the robot. But actually, the most important layer in the fuzzy neural network is the fuzzy rules layer, because the fuzzy rules control the input to be the output. And this is kind of fuzzy rule, which called as TSK if then fuzzy rule. You can see it, the X1 is the input if it is in the fuzzy set mu I1 and until the Sn is in the fuzzy set mu In. Then the consequence of this fuzzy rule is AI. So what is the mu I, the fuzzy set? Actually, it is represented by the Gaussian membership function. This is the Gaussian matrix function, and xj is the input variable for the Gaussian matrix function muij, and mij and the sigma ij are the center and width of the fuzzy set muij. So for one fuzzy rule, there will be the m, sigma, and the a are the parameters of one fuzzy rule. But there are so many fuzzy rules in the fuzzy neural network, so when we combine all the parameters, then it became the solution for the fuzzy controller, which is represented as an n-dimensional vector.
Yes.
So the optimization algorithm is trying to find the best solution. So what is the optimization algorithm?
There are actually many optimizing methods. One of the most popular current method is particle swarm optimization (PSO). This picture shows a visual graph of PSO. PSO is a searching strategy that uses a swarm of particles to search the best solution in a solution space by moving the position of a particle. So a particle here has the position, velocity, and physics value. The position of the particle is the location of it in the solution space, which is equal to the parameters of the fuzzy neural network. And the velocity of this particle represents the moving speed and the direction of the particle. There are two major concepts in PSO. The first one is personal best. Personal best has the previous position of the particle with the best fitness value, like here in this picture. And the global best is the particle with the best fitness value in the swarm, like here. PSO also have advantages and disadvantages. The most important advantages is that it have a very good converging ability, which means it has a predictable moving direction of all particles. But the disadvantage of PSO is that it has a bad exploration ability, which means it has limited searching area. So this disadvantage make PSO easy to trap in the local minima. The current motivation here is to solve this local minima issue of PSO by enhancing the exploration ability. So Guanghua, what is the solution for solve this issue?
So actually, there are many typical solutions for local minima issues. Two of them are the DGPSO and eGPSO, which are all the group-based particle swarm optimization algorithm. But we would like to find an algorithm which have the better performance, which means it maybe have better convergence or better exploration ability. And then we find the firewall algorithm, which is introduced by Tang and Jun 2010. It is said it has the advantage of diversity in generating offspring, which help escaping from the local minima. And also you can see it from the right side of the screen. This is a figure shows the convergence speed of firewall algorithm. The convergence speed actually is excellent for the firewall algorithm. You can see it from this figure. And this figure shows the visual graph of the firewall algorithm. You can see the searching path of the firewall algorithm is actually a circle. So it's different than the PSO because the exploration, which means the circle of the firewall, makes the possible position areas of offspring larger than PSO because PSO just search like line.
However, the federal algorithm also have some problem. The most serious problem is its computational cost, because federal algorithm is based on evaluating a large number of new particles. Especially in our robot control area, the evaluation of particle is a time-consuming task. So this disadvantage is quite serious. One of the exploration by Chen et al. Has tried to combine the Farrow algorithm and PSO, but their proposed model PSFW also have a very high computational cost. So the motivation here in our research is to use the concept of exploration, use the concept of explosion of firewall algorithm to boost the exploration ability of PSO. At the same time, we also want to keep the computational cost of our proposed algorithm as low as possible. So Guanhua, what is the methodology used in our research?
The methodology we come up with the motivation is the vibration-based particle swarm optimization algorithm, which has the enhanced convergence ability and boost exploration ability. You can see it here. This is the traditional PSO, and this is the VBPSO. The traditional PSO searching path is predictable and narrow. You can see it because every particle is trapped by the personal best and global best, so that the path of it is predictable. So we add the vibration factor in the PSO to be the VBPSO, so that the searching area is widened, and with this vibration factor, the exploration ability is enhanced. So how the vibration factor be designed?
So the vibration factor is actually the major concept of VBPSO, which can be defined with this formula. This formula actually has three terms. First term is the direction. The second term is the random number range from 0 to 1. The third term is the amplitude, which define the vibration amplitude. This amplitude is defined by the formula here. Because the better the fitness, the higher the chance of the particle trapped in the local minima, which require a larger amplitude. This formula ensures that as the particle moving towards the global best, its vibration amplitude increases. However, the amplitude also need to be limited. So that's the reason we add a BJ here. Because too large of the amplitude makes the algorithm no different from random choice. So this boundary, Bj, of the amplitude is defined by this formula that will ensure that the amplitude only varies within a reasonable interval. Okay, we have discussed how this amplitude term is defined. So Guanhua, how this direction factor is defined?
Actually, the direction is really important for the VBPSO, because the direction of the vibration is as same as the direction of the velocity of the particle. Because the reverse vibration can decrease the convergence speed of the algorithm, and the positive vibration can push the particle to the global best faster, so that this can improve the convergence speed. And we have this designed formula for VBPSO. And for each particle, their velocity is updated with the standard PSO algorithm. You see here, t at 1 velocity actually is only impacted by the personal best position and the global best position. We do not add the vibration factor into the velocity updating process, but into the position updating process. This is because the velocity updating is an incremental process. A change of the velocity will have a long-term unpredictable impact. And now we add the vibration factor to update the position of the particle. This is the workflow of VBPSO. It shows how VBPSO process. First of all, the swarm will be initial in the beginning, and then we will calculate the vibration factors of all particles. And then next step, we will start the iteration, which will evaluate all particles of a swarm. We will get the particle and update its velocity. update its position with the velocity and the vibration factor. After we get the position, we will evaluate the particle. After we evaluate all particles, we will evaluate whether the particles is satisfied the success condition. If it is satisfied, then we will stop this process. If it is not, we will back to the beginning and start a new iteration until it finds the best solution or it meets the maximum iterations number. So how the VBPSO performed in the testing result?
Yes, we trying to evaluate our VBPO by comparing it with traditional PSO and the Farrell algorithm. So the performance of them are evaluated by the number of iterations, which is generated on the fly during experiments. All the three optimizers are tested for 100 times, and we record the number of iterations for those tests. For each iteration, they have 50 evaluations or runs, and each particle is evaluated once in one run. We also define the failure standard for experiments. If an experiment fail for 80 iterations or 4,000 runs, this experiment is considered as fail. And on the other hand, if the robot can move for 4,000 steps, this experiment is considered as successful. The first step means the fitting value of the particle equals to 0.00025, which is the inverse of 4,000. After we getting the evaluation data, we can see in this table the performance of these three algorithms is compared with average iteration, maximum iteration, standard deviation, and numbers of failure. PSO have modest average iteration, the modest standard deviation, and it fell only for once. On the other hand, the Farrell algorithm very, very high average iteration, very high standard deviation, and is likely to fail. Because we have tested it for 100 times, 80 of them has failed. It means most of the experience of Farrell algorithm has failed. VBPSO, the proposed model, is the best one with the lowest average iteration, which is around 10. The lowest standard deviation, it is below 10, and it never fails. Another way to see the testing result is through this box plot. Those dots in this box plot represent the extreme values of those numbers of iterations, and the box here represent the modest value, the values from 25% to 75%. So this pictures means the less the number of outlier, those dots, and the narrower the range of this outlier, the better stability of the optimizer is. So we can see this in this picture that the VBPSO is more stable and faster than the other two optimizers. So we have, after we give this test result, I think we need to show the video demonstration of our proposed model.
This is the video demonstration for the VBPSO during the training process. You can see at the beginning, the robot is trying to learn the warfaring behavior, but it just failed. They keep running. And after a while, then this robot learned the warfaring behavior and just go around the obstacle, and it can just run more than one round. So it is trained as success. And then we get the result of the trained fast controller. We put it to the testing environment. So now let's see the training result. Now the robot can following the obstacle more than one round, and then just keep going through round, Actually, if you just put it run, it can run until you put it stop. So the result of the VBPSO is success. So this is all we done in this project. Now let's get the conclusion.
Yeah. The conclusion of our research is that we propose the vibration-based particle swarm optimization, VBPSO. This algorithm is an optimization algorithm for the fuzzy controller applied to robot navigation training. The algorithm is motivated by the Federic algorithm, and it combines with traditional particle swarm optimization. The vibration term of VBPSO that added into position updating calculation of PSO help it escape from local minimum and increase the converging speed. The training effect of proposed model is compared with PSO and the Federic algorithm. The training have verified that our proposed VBPSO have a very high performance.
However, the training environment is quite simple with only one obstacle, so that the behavior of the robot learned is limited. The future research direction may include applying VBPSO on other complex environments to learn more behavior knowledge. Furthermore, we will test the VBPSO on solving other optimization problem to test its adaptability. In addition, the future study may include combining the VBPSO with multi-object optimization methods to extend its feasibility.
Those are the references we included in our research. Yeah.
Thank you.
Thank you.